You've got work to speed up, and Python hands you 3 tools: threading, multiprocessing, and Asyncio. Pick the wrong one, and you'll write more code to run slower than the plain loop you started with. Move a CPU job onto threads, and it gets slower, 5.1 seconds, up from 4.9. Move an I/O job onto the same threads, and it's 28 times faster. Same tool, same machine, opposite verdicts. Here's why. Everything turns on one question: is your work CPU bound or I/O bound? CPU bound means the processor is busy, crunching numbers, never waiting. I/O bound means the processor is idle, waiting on a network call, a disk, a database. We run the same 2 workloads through every tool. The ranking flips between them. First, CPU bound, 20 million pure Python math operations. Threads make it slightly slower, no speed up at all. Multiprocessing gets a real 3.4 times, spread across 16 cores. But the actual winner runs 0 threads and 0 processes. We'll come back to it. Now I/O bound, 64 calls that each wait 50 milliseconds. The ranking inverts completely. Threads, 28 times faster. Async, 57. And multiprocessing, the CPU champion, is nearly the worst tool here. One thing explains both tables: the GIL, Python's global interpreter lock. Only one thread can run Python code at a time. Full stop. So on CPU work, your 16 threads just take turns, no speed up. But the lock is released whenever a thread waits, so on I/O, all the waiting overlaps, for free. That one rule is the whole inversion. So the tools sort themselves out. Threads are for waiting, not computing. Processes get real cores, each with its own interpreter, but you pay in startup and pickling. Async scales waiting to thousands of tasks on a single thread. Remember the CPU winner that ran no threads at all? It's numpy, vectorization. Push the loop into C, and it beats 16 processes by 3 times. No GIL to fight, no processes to spawn, no data to copy. For numeric CPU work, the fastest concurrency is often no concurrency. Now the twist. In Python 3.13, the GIL became optional. The free-threaded build removes it, and threads finally run in parallel. Same CPU workload, 16 threads. 7.5 times on 3.13, just under 8 on 3.14. It even beats multiprocessing because threads share memory, nothing to copy. The catch is a single thread tax, but it's shrinking fast. 1.5 times on 3.13, down to 1.2 on 3.14. You opt into a separate build and check it with one line: sys dot is GIL enabled. So, classify the work before you touch a library. Threads for I/O, processes for CPU, async for I/O at scale. And vectorize before you parallelize anything numeric. The first question is never how many cores. It's whether this code should be doing the work at all. Threads, processes, async, vectorization. 4 tools, not 4 competitors. Each answers a different question about your work. Match the tool to the shape of the problem.